put up the record also, that is better. Optical isomerism in coordination complexes. This is the topic. Okay, ma. So in this, what you have to know is how to draw the optical isomer. If you practice that, there are some 2-3 examples are there, that if you practice, that is sufficient. You don't have to worry too much about the other things. So the first one is dextro uh, dextro COEN twice, COEN thrice. The ion is having a charge of 2 plus. So this is the one that is CO3 plus. Sorry, this is CO3 plus. COEN thrice 3 plus. This ion structure we have to draw. So what is EN? EN is ethylene diamine. Ethylene diamine. En is ethylene diamine. So what is ethylene diamine? You know this. It is like this. This is our ethylene diamine structure. Now, how to draw this? So we'll do that. CO, you had to put something like, so this is how they draw in your text generally. So this is how they draw. This is okay. This is how they show. So I'm not comfortable with this. I'll tell you the exact way of drawing this one. See, you put one nitrogen here, one nitrogen here. This actually the way we have to draw the structure. Okay, octahedral means these two will form the apex. Okay, now draw this. Draw like this. Again, one NH2, one NH2. Okay, and these two are connected by our carbon backbone. To draw like this, I think they have to show. It may get complicated. That's the reason they are not showing like this. Is actually you got to draw like this. So if you draw like this is the correct way of drawing the structure. And now this one will be like this. So you have this NH2, NH2. Okay. So this is how you actually have to represent. This is CO in thrice. So having a charge of 3 plus. Okay. Now you have to draw the mirror image of this one, mirror image. So how to do the mirror image? Exact mirror image you have to draw. You have to practice this. CO. You have this NH2. NH2. This is CH2. CH2. And here NH2. So this forms the, okay. So, oh, I'm mistaken. So I'm mistaken. Just a minute. I'm mistaken. So I have to draw the mirror image. Fine. So this is CO. This is NH2 on the top. And now this will come here. here. So this is my NH2. You have this one as CH2 and CH2, both are bonded like this. This is my one COEN price. And now this entire thing will come to front here. So that's how we have to draw. That's the mirror image, right? So this is my NH2 again. And you have, this is my CH2 backbone. And then you have this as NH2, and this how it is connected. This is the front side. The next one is like this. This goes to the back. So this is NH2, NH2. This is like this. So like what we have drawn for the oxalic acid, the similar way you have to draw. So this structure you have to give some practice. You have, unless you give a practice, it's very difficult for you to solve these structures. So in fact, the other way I will, you can note, in fact, the other way to simply draw is like this. So first do like this. So first do like this. You put all N all over. You put all N all over. So the best way I'm telling. So, okay, this one. This one like this. This one like this. H2, 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 H2. Okay, so you give the mirror image. You have CO, NH2, NH2. So it will come like this. N NH2, 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 like this. Like this. You have to give some little bit of practice in order to solve like this. Okay, ma?
Okay, sir.
Okay, noted. This is one complex which you have to remember. Overall, for this, you put 2 plus. Overall, for this, you put 2 plus. These are optical. This is called dextro isomer. This is called levo isomer.
Okay, sir.
Next one. So let's try this one. CO Cl2 COCl2 COCl2 NH3 twice En NH3 twice En. For this complex, we have to write optical isomers. Okay. So let's put this. So it's like CO Cl on the top. You can have Cl at the bottom. That is one thing. Okay, they have taken specially. Okay, we can have this one also, no problem. You have uh, just a minute, for this you make it okay. You can have like this. So both NH. There are different ways of drawing this structure. So one of the form will write. So, and you have En. And H2. So this is one way. You can have the mirror image of this one. So you can have the mirror image. So that is CO, NH3 like this, NH3 like this, Cl, Cl. You have NH2, NH2 like this. This is one way. This is the one way of drawing the structure. Okay. If they give for this, especially they will provide you one structure. For this one, they provide you one structure. They provide you one structure at least. You have to draw the other mirror image. Okay, this is one thing, Amma. Other possibility also I'm drawing. One CL on the top, one CL at the base position. That is another possibility. Like this. This is the one CL on the top, one CL at the base position. You can have NH3. This is also other isomer. This is also the other isomer. Okay, ma. Now,
Okay,
for
sir.
this mirror image, CO, you have Cl, NH3, Cl, NH3, like this, NH2, NH2, like this you can have. So this way you had to little bit give the practice. Is you had to assume that this dotted line is a mirror. This is the mirror. And then you have to draw the structures.
Okay, sir.
Okay, ma? Now we'll move on. Mm, no. The next isomer you have to practice is PrCl2En twice 2 plus. PrCl2En twice 2 plus. This is the other isomer we have to practice. So it's like this. So it is PrCl. So one NH2 here, another NH2 here. Let me put like this. Then okay, the other one is like this. NH2. PrCl2. The other position here with you the chlorine, and here the required NH2. So this is how you have one. So we have to draw the mirror image of this one. PrCl. On top we have chlorine, and then you have NH2. Here NH2. This one, and again Cl here. No, 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 no. Did I do the mistake? Yes, of course. Yes, of course, I did the mistake. I did the mistake. So here we have PR, Cl on the top. This Cl comes to the front. Okay. So this one NH2, and you have NH2 here. Okay. This like this. Okay, this is connected. Now this goes to the back. And this is NH2, NH2. Yeah, that's how you have to draw the structures. This mirror image you have to check. Even I am a little bit confused on doing that sometimes. You have to check all the time. This is sufficient. If these three structures you should be able to draw in the optical activity side, this is sufficient.
Okay, sir.
Okay. Now bonding. Valency bond theory is what this is. It was put forward by Linus Pauling. Uh, the first thing it says that it was done by L. Pauling, Linus Pauling. His name is scientist. He did that in he put forward this theory in 1930. This theory is put forward. What are the main postulates? Is a central atom or an ion. This is called valency bond theory. Central atom or ion makes available required number of makes available required number of empty orbitals. And these orbitals will undergo hybridization. Undergo hybridization. Okay. This hybridization develops the different kinds of structures. Okay, ma. So there are different types of hybridization, SP, SP3. Okay, that's the different thing. Okay, then when you have SP3 hybridization, you will end up with the tetrahedral structures. When you have DSP2, you have a square planar structure. DSP, when do you get DSP2? All these things I'll explain. Square planar structure. And when you have SP3D, you have octahedral. So these are the some of the things what SP3D is, sorry, SP3D, D2 is octahedral, and SP3D is trigonal bipyramid. And you have the further D2SP3, that is another case of octahedral. D2SP3 is the other case of octahedral. These are the structures I will let you know. In all cases, I'll explain all the cases. So with examples we'll do.
Okay, sir.
Now, the first example what we take is CONH3 6 times 3 plus. CONH3 6 times 3 plus ion. This is an octahedral complex. So first thing is, what is the central metal ion? Central metal ion. Central metal ion is cobalt 3 plus. That is our central metal ion. So we'll solve this slowly. So first thing is, we have to know this one: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So this one we have to know. Scandium is D1S2, titanium D2S2, vanadium is D3S2, chromium is D5S1, manganese is D6, D5S2, manganese, and iron is D6S2, cobalt is D7S2. Okay, so the cobalt configuration is 3D7 4S2. So cobalt configuration, you have the outermost shell, that's it, 3D7 4S2, that's what we write. Now we see this cobalt 3 plus means 3 electrons will go off. So you will end up with a D6 type configuration, that is 3D6. Okay, 2 electrons from here, 1 electron from here. So D6 you will end up. So let us see what happens. 4, 1, 2, 3, 4, 5. Okay, we draw this 1, 2, 3, 4, 5, 6 electrons. This is how you have. And you see the s orbitals, they are vacant completely. This is the 4s. Okay, 4s orbitals, and these are, and after this you have the p orbitals also. You have the p orbitals also, which are vacant. Now what happens is, how many ammonia molecules are coming? There are 6 ammonia molecules which are coming closer to the cobalt 3 plus, okay, to make the bonds. So this NH3, what it does is, it will start, it is having an ability called, it's a strong field. It creates some kind of a strong, in fact, it's a kind of electric field, okay? Electric field. And the NH3 can be treated as, how, why it creates an electric field is like, you have lone pair on the NH3 that creates an electric field for you. So, so when it creates the electric field, it will repel these electrons uh, and force these electrons to pair back. So this one, these 2 electrons will pair again, once again, it forms like this. These 2 electrons will pair once again, and it will go back to something like this. And now 2 d orbitals, because of this is called forced pairing. Okay, because of this, the electrons will move back and it will vacate 2 d orbitals for you. So 2 d orbitals, and then is from this 1s orbital is coming, that's a 4s, and then 4p will be there. Okay, the 4p, all the p orbitals. Okay, now you check how many number of orbitals. 1, 2, 3, 4, 5, 6. 6 orbitals are vacant for 6 ammonia groups, 6 NH3 groups. So these 6 orbitals will combine to form, the first is 2d orbitals which are coming. So it is d2, 1s orbital, that is s, and then there's 3p, d2, sp3, hybridization. Okay, ma? Got it?
Yes, sir.
Okay. Now this D2sp3 hybridization, how many orbitals will come? 6 hybrid orbitals. 6 hybrid orbitals. 6 hybrid orbitals are coming because of this D2sp3 hybridization. Now let me clear this. Can I clear? Want to make a note?
Note
Anyway,
this
I'll
one.
try to send the record of this to you. Uh,
Okay, sir.
so you have the D2S, that 6 D2sp3 hybrid orbitals are there, right? Hybrid orbitals. They will start orienting in the octahedral fashion. So it is CO. They orient in the octahedral thing. Means like the 6 orbitals are oriented, the 4 orbitals in this base positions, and 2 orbitals, one up and one down. These are all D2sp3 hybrid orbitals. And for these vacant orbitals, the nitrogens from ammonia will donate the electrons to form coordinate covalent bonds. Nitrogens from ammonia will donate electrons. So you can write the lone pairs on nitrogens in ammonia will donate the electrons, will donate the electrons to these vacant D2sp3 hybrid orbitals to form coordinate covalent bond. Coordinate covalent bond. Covalent bond. So this is what the information unit. And now this forms, this is an octahedral complex. So the complex what we have is an octahedral complex. You can see the octahedral when you join the things like this. This is the octahedral complex. This is the octahedral complex. This is the octahedral complex what you have. And here, this is also called inner orbital complex. Inner orbital complex. Because as you have the in as inner 3D orbitals are used. Okay, inner 3D orbitals are used, so it's an inner orbital complex. So that is, if in fact it's like if n minus 1 d orbitals are used, especially n minus 1 d orbitals are used for hybridization. For hybridization, it's called inner orbital complex. Inner orbital complex. Okay, ma. So these are the some small fundas which you have to remember. Once noted, please let me know.
Noted, sir.
Now we will see a case of the outer orbital complex. So suppose you have COF6 3 minus. This is the case 3 minus. This is an outer orbital complex. I will tell you why. Now it's the same. Cobalt is having the same oxidation state, cobalt 3 plus. So we can repeat the earlier thing, but there is a little bit of difference from the previous one and this one. 1, 2, 3, 4, 5. So you have 1, 2, 3, 4, 5, and 6. But you have the next one. Okay, you have the 4s. This is the 3D, and you have 4s, and you have 4p. This is 4p, and you have the next one we consider is 4D. Also, will consider. I'll tell you why we have to consider this. 1, 2, 3, 4, and you have 5, and this is the 4D. Why we have to consider 4D? See here, like the earlier case, what the nitrogen in ammonia it has done is NH3. What it has done is it allowed this electrons, it has pushed back, and it does the forced pairing. But F minus can't create the enough field to force pair. So you have the 3D electrons will stay as it is. So here 3D orbitals will not participate in hybridization. That's most important thing. 3D orbitals will not participate in hybridization at all. They will not, because the reason why is that the F minus ion is there. No, F minus, it cannot create the enough amount of field to force pair the electrons. So the reason you cannot, it will not do. So what you have is that the electrons, the F minus will utilize these orbitals. You see, the 3D orbitals are not utilized. Here, this is called, they are outer orbitals. There, so it's outer orbital complex. Outer orbital complex is especially is the case where even the ND orbitals are used. Okay, ND orbitals are used. When ND orbitals are used, that's an outer orbital complex. N-1D is used, that is inner orbital complex. As simple as that. Now, you see the 6F minus ions, they transport the electrons to this. Okay, 1, 2, 3, 4, 5, 6. Here we write the hybridization as sp3d2. The earlier one was d2sp3. D2sp3 is the case of inner orbital complex. Inner orbital complex. Inner orbital complex. Okay, ma? And now this is like sp3d2. This is outer orbital complex. I hope you understood the difference. So d2 is coming before, that is inner orbital complex. sp3d2, that's the outer orbital complex. That's the difference. Clear, Amma? So we draw that. How does it look like? How does it look like? We draw that. So you have the cobalt. Simple. The fluorine on the top, one fluorine at the bottom, and the fluorines like this. They form the octahedral positions, and that's how it is. So that's the octahedral. That's the octahedral positions. So this is my, it has a charge of 3 minus. We should not forget. This is my CO F6 3 minus ion. There is another thing what we have to know is that the magnetic behavior, that I'll let you know later. Once you finish this one.
Yes, sir.
Okay, man. Right. Now, now you have the. I'll tell you about the magnetic behavior. Magnetic magnetic behavior. What is this magnetic behavior? So remember 2 points. If unpaired electrons are there, are there, if unpaired electrons are there, it's paramagnetic. The spin on, there is something called spin only. Just a minute, Amma. Just a minute. Just a minute. My daughter, she is disturbing a lot. Just a minute, Amma. Don't mind. Padam, no. Padam. Padam. Paramagnetic. If unpaired electrons are there, it's paramagnetic. There is something called spin only magnetic moment formula. What is spin only magnetic moment formula? That is square root of n into n plus 2 4 magnetons. So that n is number of unpaired electrons. That is one thing. The second thing is that if all electrons are paired, that means no unpaired electron. No unpaired electron is there. It is diamagnetic. If no unpaired electron is there, that's diamagnetic for you. That's diamagnetic for you. Once you can know, you can have a note and then I'll clear. We'll solve some examples.
Okay, sir. Okay, sir.
Right.
Completed, sir.
Yeah, good. The next one is we have the square planar complexes. Square planar. And we have the next one is tetrahedral. And we have some tetrahedral, square planar tetrahedral. And then we have the magnetic behavior. After this, we have some crystal field theory. Crystal field theory. After that, the chapter is over. So, Amma, if possible, I will set up another class today evening. Is that okay for you? Oh, we have metal corners. That is the next one. Metal corners and stability of the complexes. That is
What
one.
time, sir?
Maybe at around evening, something like 4:30. 4:30 to 5:30.
4:30 to 5:30 is okay, sir. 5:30 to 9 I have class.
Okay, ma. Okay, 4:30 to 5:30 is okay, right? Evening. So
Yes, sir.
if
Yes,
possible,
sir.
I'll put up. Why? Because tomorrow I'm not sure whether I can take the class or not. That's why only for that reason. Today itself I want to finish the tomorrow class. Actually, Saturday Sunday I thought. So that today itself, if I put up the 2 sessions, Sunday, if possible, I will put up. Otherwise, I will not put. Okay, ma. So only for that I am asking. If it is okay for 4:30 to 5:30, that's fine, right? That's fine for you. So that we can complete this
Okay.
chapter. We can complete this chapter. Amma, can you just log in once again, please? Log in once again. Once again,
Okay, sir.
please. Just log in once again. I will change my internet. Just a minute. So this is like unstable internet. Sometimes you may getting that this is getting stuck sometimes. As far as I know. Okay. We'll change this once again.